I ran into a bug the other day while writing unit tests for the bytecode interpreter, and I thought it would be interesting to go through the steps that I used in Visual Studio to diagnose the problem. I created a branch that has the repro case for the bug in case you want to follow along at home. Here's the BitFunnel repository. It's at github.com/bitfunnel/bitfunnel. And if you go to the branches, there's a branch here called SEHBug. And this has the repro for the bug. So let's just get the computer configured so we can see the bug. So I'm in my Git repo here for BitFunnel, and I'm going to check out the SEH branch. So git checkout SEHbug. I'm going to switch to the branch. Now I'm going to start Visual Studio. Now in BitFunnel, when we're using CMake, the Visual Studio solution file is in the build MSVC directory. So I'll just say start, build, I hit tab, and I'm going to want bitfunnel_cmake.solution. So let's start this up in Visual Studio. Now, since the last time I built, I have changed the repo because I switched us to a branch. So it's possible, in fact quite likely, that this build is out of date. I find with CMake and Visual Studio, when you change the build on it, that it's always a good idea to right-click on the zero-check project and do build, and wait for that to finish. And sometimes when it finishes, it'll ask you to reload the solution because maybe another project has been added or removed. Doesn't look like that happened in this case. And then do all build, and so we'll do that. And let's see. I think in this case, it's going to build everything from scratch because I didn't have a build already set up. So we'll just wait for this to go through the build here. It shouldn't take too long. I can see from this green progress bar that we're about 2/3 done. Getting a little closer here. And it's nice that BitFunnel actually builds pretty quick. I've been on a lot of projects that take a long time to build. And looks like we're done. Okay, so how did I know that there was a bug? I know there's a bug because I was getting ready to check in and I thought I'd run the unit tests, and that's where I saw the failure. So in CMake, from Visual Studio, we can run the unit tests by just clicking on the Run Tests target and right-clicking and doing Build. And build makes it sound like it's actually building something, but what build means is run this target, and this target runs ctest. So when I say build, you'll see down here in the output window that it's showing the results of all the tests. And you can see that not all the tests ran, one of them failed. And in fact, the test that failed is right here, it's plan test. Now, when I run the test from the build target in ctest, I can't actually see the output of the tests. These are gtest tests, and they should actually print out which test inside the suite failed. So the way we're going to see the output is I'm actually going to run plan test itself. So let's go find plan test. In BitFunnel, the libraries are organized under the source folder, and I'm just going to close some of these under source. And we have plan, and under plan is a test directory. And that is the executable we want to run for plan test. So to run this executable, I'm going to right click and I'm going to say set as startup project. Now I can press a button to run it, or I can use a control key, and I'm just going to use control keys. I'm going to hit Control F5 to run the test. And you can see that it printed out a whole bunch of output, especially showing that the test failed. And let's just take a look at the first instance of a test that failed. And this test, because I'm in the middle of developing it, it has a lot of console spew. But in general, we shouldn't have that. So here's the first test that failed right here. It started this test called byteinterpreter.androidjz_delta0. And then immediately afterwards, it had an error. And the error is an SEH exception. Just out of curiosity, I already know what this is, but let's just take a look at what happens if you search for this. And we get to this website, how to fix an SEH exception with code COOX5. The funny thing is this web page is just generated to basically lure people in, and it doesn't say anything useful about it. In any event, let's get on to actually fixing this instead of going to the web to figure out how to fix it. The first thing I like to do when I see an error is I like to narrow down the repro case. So this is actually running first we were running all the test suites. Now we're running only one test suite, but we're running all the tests in it. Let's narrow it down to only run the first test that failed. This will help us if we're single-stepping through it or rerunning the program with breakpoints, that we don't have to have it stop in breakpoints on a whole bunch of other tests. So I'm going to just right-click on this to copy it, and I'm going to go over to my test project, and I'm going to right-click and go to Properties. I'm going to go to the debug dialog, and I'm going to go to the command arguments. And here I'm going to tell gtest to only run one test. I'm going to do --gtest _ filter equals, and then I'm going to paste in the name of the test that I want it to run. And now let's try running again. I'm going to hit Control F5 to run. And you can see this time it's only running byte interpreter and row JZ delta 0, and that test is failing. So now we've got a smaller repro case. And I also notice if I go out of here and I hit Control F5 again, it seems like it repros 100% of the time. So that makes our job a little easier. So now the question is, what the heck is this SEH exception? What does that mean? An SEH exception is a Windows structured exception handler exception. This is not a C++ exception. It's generated by the operating system, usually when you do something like read memory that you're not allowed to read. So let's run this in the debugger and see if we can get some more information on what's happening. The reason we don't see any dialog here is that gtest is catching the exception and failing the test. So to go in the debugger, we can press this button up here, or we can just press F5. I'm going to press F5 to run the debugger. And the program starts up, and immediately it fails. It says exception was thrown, read access violation. It says a little bit about the line of C++ code where it happened, and gives us some options. We can break, continue, ignore. We're going to hit break because we actually want to look at the problem in the debugger. Now, I'm not really sure why this is showing up in disassembly view. I'm just going to close it and double click on the stack frame again. And now we've got C++ view. It was probably in the disassembly view because the last time I was running the debugger, I was looking at the disassembly view. So what we're looking at is, this is the call stack over here, and this is the most recent frame on the call stack. You can see all the way at the other end, here's main. So the program started at main, and it drilled down through all of these frames and finally got to here. And when it got to here, on this line, we crashed. And we crashed because we were accessing some memory that we're not allowed to access. So the only memory that's getting accessed here is we're dereferencing a pointer. So somehow there's some bogus value with this pointer. And we can see when I hover the mouse over here that this basically it shows question mark as the value at this memory address. And if I try to open it up, it says unable to read memory. So when I'm floating over the tooltips here, the debugger is actually throwing the same exception and catching it. We can look at this in the memory viewer to see. So if we go to the debug windows, and there's a zillion really interesting windows under debug, and I'm just going to go down to memory, and they actually give you 4 of these, so you can have a couple open at a time. I'm going to open one of these, and it docked it up at the top. And I'm just going to type in the name of the variable that I want to look at. So m underscore, oh look, I've already typed it in, m underscore freelist head. And we can see what it points to is all question marks. Now, you might wonder, what does it look like when memory is valid? I could put in this pointer, and you can see that at least it was able to read values out of here. Whether these are valid values or not, it's a little hard to know without knowing what's supposed to be in the class, but I'll say that they at least look kind of structured. So let's go back to m underscore freelist head. So this is some pointer to a memory address which isn't mapped, and that's why we get an exception for our process. We can't look at this address. So let's take a look at the code and see if we can figure out what's going on. So we're in this block allocator, and we're in the allocate block method. And what this block allocator is doing is it has a free list of blocks, and it's looking at the head of the free list and saying, do I have another block? And if I don't, it's just going to throw an error saying it doesn't have memory. If it does have a block, in other words, the free list doesn't point to the null pointer, it's going to save the free list, and then it's going to advance the free list to the next block on the free list, and then it's going to return the thing that the free list was previously. So maybe a diagram would help this. So I'm going to do window R for run, and I'm going to run MS Paint, which is the Paint program. And let's just dock this off on the right side, and we'll dock Visual Studio on the left. I just did that by, I took the window and I just dragged it against the right edge of the screen. And and that just made it take half the screen, and Visual Studio's got the other half. So what we have for this, and let's just set up a pen. Let's use red and see if we've got a good size. So we have this variable. Let me get my my drawing implement here. So there's m underscore free list. Let's see if I can write m underscore free. Can't write very well today. Free list head. And this is the pointer to the head of the free list. And this block allocator, it started out with a big block of memory, consecutive bytes of memory. And in its constructor, it chopped this memory up into a whole bunch of pieces. And then in each piece, it put a pointer to the next piece. So the free list, it made the free list point to the first block. And then the first block had a pointer at the beginning that pointed to the second block. And the second block had a pointer that pointed to the third block, and so on. And somewhere down at the end of the free list, the pointer was null pointer, which indicated that we're at the end of the free list. And so what this code is doing is it allocates the block, which is at the head, and then it wants to update the head pointer to point down below. So in other words, let me change my color. What happened was we got a variable called block. Oops, I didn't change the color. We got a new variable called block. We made block point to where free list head pointed to. And then free list head went and it dereferenced the pointer that was at the beginning of free list head. So there was a pointer here. Oops. In here there was a pointer, and it dereferenced that, and it made free list head point to that pointer's location, which was now the next block. And then block was returned, and it was given to someone who could write whatever they wanted into the block. And so that's how this code was supposed to work. Now the puzzling thing going on here is that free list head has a invalid value. So let's just take the blue stuff out of here. So the question is, how did the value get wrong? So I think the best thing to do is let's set a breakpoint at the beginning, and let's set beginning and the end of this function. And let's rerun it, and let's see, did this happen on the first iteration, the second iteration? Where did it crash? So I'm just going to go to full screen here, and I'm going to hit the restart button. And we'll start here. So, and then I'm going to hit continue. So I hit continue, and you can see this yellow pointer arrow shows where we are. So the first call through this did not fail. I hit continue. We're back up at the top here now. The second call, we're in here. It didn't fail. So I'll hit continue again. We're back at the top. The third call, oops, the third call failed. So this is a really nice thing because we don't actually have to single step through a whole bunch of code or engineer how to get past 1,000 iterations to figure out how this went wrong. Basically what we're seeing is that if we go to our picture, we were able to allocate the first block, and let's see. We were able to allocate the first block and set this pointer to the second block. And then we came through the second iteration, and we were able to allocate the second block, and we set the pointer to the third block. And then when we came along to dereference this memory location, we found out that we couldn't because the pointer had an invalid value in it. So on the third iteration, we had the value that we picked up from here. So somehow it looks like either that value was incorrect when we initialized the class, or that value got corrupted somehow. So let's see if we can figure out which case it was. So I'm going to rerun the program again, and I want to look at the data structure right from the beginning. So here's the data structure is all set up. I'm going to take m underscore free list head, and I'm going to control drag it up into here so we can look at what is at that address. And what we're seeing here looks like a plausible chunk of memory for the first allocation out of some block allocator. Like it looks like the memory was probably all zeroed out when the block allocator was made. And it looks like there's something like a pointer here. I'm going to right click, and I'm going to set the view to 8-byte integer so that we can take a look and see if this is actually a pointer. This kind of looks like a pointer. It's a similar number to the address of the block. And we can actually do another thing to check. I'm just going to copy this. I'm going to open another debug window if I can find it. There's a window here called the immediate window, and it allows us to evaluate expressions. So I'm going to take the second pointer and I'm going to subtract off the value of the first pointer. So I'm just going to copy paste that down here and see how far apart these are. Oh, and that needs an OX before it. And these are 2710 hex bytes apart. And that seems plausible because if we open up this pointer here and we look at m_block size for the block allocator, we can see that blocks are 2710 hex bytes long, which seems reasonable. Like I said, that we started out with a big chunk of memory and we chopped it into block size spaces. So the fact that the next value here is a block length apart looks pretty plausible for the first pointer. So I'm going to open up another memory viewer because we want to look at them at the same time, both addresses. I'm going to look at the next block. So I'll just open up memory 2. And hey, look at that, it tiled it together. And in here, I'm going to paste in the value of this address here, the pointer. So hit return. And let's just right click and show this as 8-byte integers. And if you look, so if you go, let's bring this up and that up. So the left memory is showing this left block here. The right memory viewer is showing this block. And so this blue XXXX thing is the value that we have here. And actually, let's just drag this over to the left so we can see the picture in the debugger at the same time. So what I'm hypothesizing is that this set of XXX values somehow got wrong. And what I'm seeing here is that they don't look too wrong. This number here, we can check and see if this one is another 2710 bytes beyond the first one. And I'm willing to bet it is. Let's just take a look. So OX Control V minus, and then we'll paste this in. So, and again, the pointer from the second to the third block looks like it's 2710 bytes too. So it's plausible enough to believe that this was initialized correctly. So, so somehow we're getting a bad pointer out of here, but it wasn't because it was initialized correctly. So it's probably that it got overwritten by someone. So let's go back to the code and let's start just running through and seeing what happens. So we're right at the beginning. We're taking a lock because this is a multi-threaded block allocator. I'm going to press F5 to jump down to the end just to run to the next breakpoint. And then I'm going to hit F5 again, and we're going to continue till the next block is allocated. And there we go. Whenever a value changes in the debugger and it's displayed on the screen somewhere, Visual Studio will render it red. So you can see that the first block we got filled with numbers sequentially 0, 1, 2, 3, 4. Definitely has some structure. It looks like it has some meaning. It's not just random garbage. So that makes sense. And we can also see that down here in the locals window down below, a few things changed. What's really interesting, though, is that this value in the memory 2 window changed. So that was our pointer, and our pointer just got corrupted. It just got written over somehow. And I notice also that other stuff in the block got written over as well. If we make the window full screen, and let's just put this in 1-byte integer mode for a sec. I just wanted to scroll through and see what else changed. It looks like basically there was some stuff that was, there's a lot of stuff that was zeros, and then some random numbers have gotten scattered through it. So, so that's fascinating. Let me set the value back so we can see it. Well, we'll see it on the next run. Oh, here's the pointer that got changed. So let's just rerun, and I'll just put my values in again. Now, every time I run this, these are at different memory addresses. So I'm just double-clicking these, and then I'm just control dragging them over. We get a different memory address each time just because the memory allocator is putting things at a slightly different address. But again, let's just look at this and see if it's reproducible. So we continue to the end, we continue, and we run around, and it gets overwritten. So let me rerun, and let's see this again. So free list head is up here, and you know, we can actually, instead of dragging this pointer in, we can just drag in this mathematical expression in up here and to see the next block. Okay, so the question is, though, what's going on? Why is it between the first and second call of the block allocator does this pointer get overwritten? So one way we can figure out is we'll just start single stepping. So I'll just single step over the block allocator. We know nothing's going to happen until we get to the end, but when we return out, we're starting to walk up the stack, and you know, notice all these methods are returning, and we'll just keep returning out. It looks like we were allocating a buffer for a slice, and if we step out of the constructor of slice, let's hit Shift 11 to just step out instead of just stepping through. We can see still nothing's changed in our memory buffer. We're in create new active slice. Let me put the call stack on the lower right so we can see. So I'm going to step out of that stack frame, and oops, and I'm just going to do Shift F11 to step out. And now we're in allocate document, and in fact you can see in allocate document, when it tries to allocate a document, it says if it doesn't have an active slice, then create a new active slice. And something to know, by the way, is if you have a yellow arrow here, this is the line that you're actually on, the one you're about to execute. If you have a kind of curved bluish white arrow, it means that the call stack is down within a call. So if I go up the stack here, this means I'm somewhere in the call for the line before. So I'm actually, you know, even though the curved blue arrow is here, it means that I'm inside the last thing, which is allocate document, which you can see. When I'm on allocate document, I'm actually at this line. I'm not in any frame below here. But so let's go out another level, and let's see, Shift F11, and we're at document ingest. We'll go out another level. And you can see here we're getting to the beginning of the test. Here we're in a method called create prime factors index. It's making a synthetic index that we're going to use to do the work with. And after setting up the index, it's filling it up with a whole bunch of documents. It's filling it up with 680 hex documents, and it's calling create document. And somehow, as a side effect of calling create document, at some point it causes this block to be allocated. So that's good. So why don't we just stay in this loop for a moment, and we'll just hit F10 over and over again to go around. And we can see that values are changing in the memory buffer up above, that as I'm adding documents, numbers are getting written in here, and these look suspiciously like document IDs. Okay, so we could just keep stepping around this loop, but and let me just go to F10, and we'll just step around, and we can see the doc IDs going up, and we can see that red values are showing up in the memory window above. If that pointer on the right is getting overwritten, it looks like we're going to have to do an awful lot of iterations, because we're going to have to go through enough documents that we've written into 2710 hex bytes before we spill over to the next buffer. So we could try to binary search the execution. I could put some conditional breakpoint in and say, let's go halfway through the doc IDs and see if that causes the problem. Let's then go through a quarter or whatever until we got there. But I think there's an easier way to do that, and that's with a data breakpoint. So we're interested in stopping when someone writes to this address. So what I'm going to do is I'm going to copy the address, go to the breakpoints window, and I'm going to make a new data breakpoint. I'm going to paste in my address. And I want to stop basically if there's a write to this address. And I want to treat it as an 8-byte write. So if anything writes to any of the 8 bytes, I want to know about it. So I'll hit OK. So theoretically, if I just hit F5 to continue, and that address is written to, the debugger will stop. So let's put it back on the call stack, and let's try that out. And there we go. The following breakpoint was hit. It says there's changes to this variable at 2710. So great. So we can see who changed that. Let's take a look. That was a method called rowtable descriptor setBit. And that makes sense. It's writing stuff to one of these slice buffers at some row index and column index. The doc index is the column. So this is like a 2D array, and it's setting a bit in this 2D array. So it's plausible that setting a bit causes that problem. And we can see that the data breakpoint happened right at this line. This is also suspicious. We're basically taking a pointer value and treating it as its dereference as an L value, and we're sticking a number into it. So that makes sense that we're overwriting something. If we hover here, we can see things like the value new val is this 9DA something number, and we see the 9DA number is up in here. So that looks like the culprit. We can double check. We can see that row, its address is something ending with 2710, which is like the address written to, and offset happens to be 0. So somehow when we were in set bit, we were writing over a pointer in the free list. So that's really interesting. So the next question is, how did this happen? Well, so let's look at the parameters. So we want to write to hex row 3C, and we want to write to doc index 6B. And somehow something's going on. Either the slice buffer is wrong, and that's why we're overwriting something, or these aren't valid positions in the buffer to write to. So let's just take a look at the row table descriptor, the thing we're in, and see if this looks valid or not. So right off the bat, I spot something suspicious, which is that the row count is 0. And yet if you go up to row index, we're writing to row 3C. If we right-click on this and I click hexadecimal display, we can turn that off. We can see that that's row number 60. So we're writing to row number 60 decimal or 3C hex when basically the data structure says there's no rows. So that's pretty suspicious. It's certainly, there's a flaw in this code in any event in that we should probably have an assert so we at least don't crash, that we die in some orderly way. So let's go fix that, and then we'll continue with the debugging session. So I just killed the debugger, and I'm now in the editor, and we're going to put an assert here, and we'll just remember this is about the middle of the file. In fact, it's marked. I'm going to include another header. We have a new assert macro that I'm trying out. We call it check. So I'll just include the check macro and go back down to around line 128. And here's our set bit function. And I'm going to say check underscore LT, check less than. And I want to say that row index is less than M underscore, and I think it was row count. So the indexes start at 0, so we want strictly less than. And then these macros are kind of like the gtest macros. You can shift into the messages. So I'm going to just say, let's set bit colon row index out of range, and put a semicolon at the end of that. And technically speaking, I should check for doc index out of range too. I'm not going to do that here just for speed. But I'm going to save this, and I'm going to build it. And let's see if that all builds, or if there's an include file path problem or anything. And not sure why the build took that long, but it finished building. So let's rerun the code, and let's see what happens now. And I'm just going to hit Control F5 to run it not in the debugger. And when we run it, the test fails, but now the test fails with an unknown C++ exception. And that's probably because of the change I made. So let's run it in the debugger and see what happens. I'm going to hit F5 to run it in the debugger. And in the debugger, we hit my breakpoint. Let's just turn off the breakpoints for a sec. And let's try running again. And I notice it just runs and ends. And the reason it runs and ends is because gtest is catching the exception. So I want to have the debugger stop whenever an exception is thrown. So I'm going to go down to this exception settings tab. And if you don't have this tab down here, you can get to it off of debug, and off of Windows, there's an exception settings window, and that'll bring it up. And I'm going to go to C++ exceptions, and it's black, so it looks like it should catch C++ exceptions, but in fact, there's a whole bunch of different ones, and black just means that some of them are checked. I'm going to check all C++ exceptions not on this list. And then I'm going to run again. And now we actually have an exception thrown. And if we break and we see where the exception was thrown, it's right here. And let's just, I'm going to hit F5 just to continue so we can see what exception it is. We'll just rerun. And it says it's a logging check exception, and it doesn't seem to print out the text of the exception, so we can't actually see what's in it. But in any event, at least we're crashing in a controlled way in that we're throwing an exception now rather than overwriting a buffer. So that's good. But now the question is, why the heck are we commanding this thing to write to a row that we shouldn't write to? And what's interesting here is when we were crashing before, we were writing to a row with a much higher number, and we were just trashing some memory that wasn't actually causing a crash. So now even writing to some lower number row index, we're crashing because the row count is 0. So for some reason, we're writing to a row table that has 0 rows. So why does the row table have 0 rows? Let's take a little, let's examine what's inside this row table. So I'll open up the this pointer, and we'll see that it's got a bunch of parameters. It's got a capacity, which is how many documents it holds. It's got how many rows tall, which is 0, which seems wrong. The rank is 1. Now, we have row tables for different ranks in BitFunnel. There's rank 0 row table, rank 1, rank 2, and I know that right before I started having this bug, I went from tests that only had rank 0 row tables to having rank 1 row tables. So somehow a rank 1 row table got created, but it wasn't provisioned with any rows. So the question is, where were the row tables created? And I happen to know, and they were created up in this create prime factors index. And so let's just go there for a sec, and let's scroll back. I'm going to hit Alt-Shift-Enter to go into full screen mode, just so that we can actually see the whole file a little bit better. Okay, so here's this function create prime factors index. The first thing it does is it makes a collection of term tables, and it adds a single term table there. I know that the term table is the thing that controls the number of rows in the row table, so I'm going to go to this method here. I'm going to just click F12 on it to go to the definition, and here's the create prime factors term table. Now, navigating in Visual Studio, if I hit Control Dash, it's my back button. It'll take me to where I was before. If I hit F12, it'll take me to the definition. I love that thing about Visual Studio that I can just hop through the code, and it's not doing text search. It's actually using the compiler to know exactly which definition to go to, and it goes through macro expansions and stuff like that. So in Create Prime Factors row table, the code that I added right before I had this problem was right here. I was basically configuring this with another row. We started with rank was equal to 0, and I said let's make a rank plus 1 row. And basically the term table has a mapping between terms and which row tables and rows they go into. And so I was saying that this particular term, which happens to be the ith prime number, the text of the ith prime number, that term should have 2 rows. It should have a rank 0 row, and it should have a rank 1 row. And I was allocating the row by, there was a variable here called explicit row count, and I was just, every time I allocated a row, I was just giving a new row number to each row. Then at the end, I went to the term table, and I told it to set the row counts. Now, the set row counts method, I'm just going to hit backspace and parentheses so that we can see the options. This is where we're telling the term table how many rows it actually has. And you can see that the API takes a rank, the explicit count, the number of explicitly mapped rows, and then the number of ad hoc or implicitly mapped rows. Let me just hit Control-Z to get back the thing I deleted. So you can see we are setting the row counts for rank 0, but we're not setting the row counts for rank 1 term table. And since we're not setting in the row counts for it, it has 0 rows. Even though in the term table we said one of your rows is going to be a rank 1 row, and it's going to have this row number. So there's 2 problems. Problem 1 is I'm using the same row counter number for each rank, and then the second problem is I'm not calling set row counts. So let's fix the second one first just to see what this is going to look like. Let me get out of insert mode or overwrite mode. I'm just going to Control-C, Control-V to copy that line. And what we're going to do is we're going to set row counts at rank 0, and then we're going to set row counts at rank 1. And so we're going to have 2 different counters. There's going to be the counter for the rows allocated in rank 0 and the counter for rows allocated in rank 1. Ad hoc row count I think is 0, so I think we can leave that alone. We can just hit F12 to see where that's declared. Oh, it's 1. Okay. And it says you need at least one of them to avoid a divide by 0 error. So Okay, so when I made these two counters, I introduced a compile error, which is what this squiggly line is, and that's because those variables don't exist. So they're up here. So I'm just going to copy this. I love this. This is one of my favorite sequences is Control-C, Control-V, V to make two things. So the first one I'm going to call explicit row count 0, and the second one's going to be 1. There happens to be a piece of arcana with the term table, which is that there's some system terms stored in rank 0, and they're not stored in the other ranks. So the rank 0 row starts at system term : count, whereas all of the other row allocations start at 0. It's just a fact about the term table. Now that I have those two variables set, I can go through and basically update where I have the compile errors. So you can see there's a squiggly error here, and it says I don't know what explicit row count is because I stuck a 0 on the end of it. After it's reported the error once, it doesn't put squiggles everywhere else. So I'm going to fix this, and basically we're passing rank in here, so we wanted rank 0, so I'm just going to put a 0 there. And now I get a squiggly error here. This one also wants to be the rank 0, so I'll put 0 there. This one we know wants to be rank 0. And here, this one though wants to be rank 1. So now I've fixed all of those. I'm going to hit Alt-Shift-Enter to go back out of full screen mode. And then I'm going to build. So I'm going to hit Control-Shift-B. And I'm in the debugger actually. So it should complain to me. Do you want to stop debugging? Yes. And now it's going to build. Okay, so now I'm going to hit Control F5 and I'm going to try running it again. And hey, look, the test passes. So what I did is I first diagnosed why we were getting the structured exception handler error. And we were getting that because we were accessing some bogus memory. We were accessing the bogus memory because we were dereferencing a pointer that had gotten overwritten. So then we used a data breakpoint to figure out who was overwriting the pointer. And we found out that our setBit method was writing on top of this pointer because we were passing it bad arguments. So we put a check in to prevent it from continuing and doing the write when passed with bad arguments. And we made the test a little better because instead of crashing it through an exception. And then we went and we looked at why bad arguments were being passed. And it turns out it wasn't that the arguments were passed, but it was that the row table was initialized incorrectly. And the arguments were just bad for that initialization of the row table. And so then we went upstream and we found the bug was in the provisioning of the row tables, that they weren't given enough rows. So this test ran. So now let's just right click here and on the project, and I'm just going to take the filter out, and I think I can just do star. Let's try that first. You can put regular expressions in for which tests you want to run. And I'm going to hit Control F5. And so now I have a whole bunch of tests passing. It looks like there's still a test failing though, which is surprising. Oh, and this test I believe is failing for a different reason. Basically, I couldn't see this test fail before because we were crashing. So I will have to fix that one, and I think that'll be the subject of another tutorial. So if you're interested in reproing this yourself, again, the steps are go to github.com/bitfunnel/bitfunnel, go to our repo, and then go to the SEHBug branch, and you can sync all the code, and then you can follow the steps in the video to try this yourself. Well, that concludes this video. Have a good day.